right, so the first thing we're going to start off with for Chapter 1, Section 2, is the cow story. I made this up, so bear with me. The text for this is in the lecture notes. So first of all, long ago in nature, there were cows. We could have 1 cow, 2 cow, 3 cows. But then, there was famine, and with famine came death. How many whole or healthy cows do you have? I could have 1 whole cow, 2 whole cow, 3 whole cows, or I could have 0 whole cows because they died. And then we had trade, and with trade came debt. And as we went into debt, we had integers. So we could still have 1 cow, 2 cow, 3 cows. We could have 0 cows, or you could owe someone a cow, or you could owe someone 2 cows, etc. And then we started butchering the cows. And so we had to explain that we did not actually want 1 cow or 2 cows. We wanted 0.25 cows, 0.3 repeating cows, which is a third of a cow, and a half of a cow, which you can still buy a half of a cow. And of course, it would be irrational to ask someone for pi cows or square root of 2 cows. And that's how we got our real number system, which is what we have and what we know so far. This is a completely and totally bogus story. Now, we're going to have, using this cow story, we're going to have some subsets of real numbers. Subsets are a set inside of another set. So, this has to do with Chapter 1, Section 2, Question 1. The cow story reviews the subsets of real numbers. So every some type of number is another some type of number. So I could ask you, for example, is every natural number a whole number? So if we did that, the natural numbers are the numbers like 1, 2, and 3, etc. Is every natural number a whole number? The whole numbers, remember, you could have 0 whole cows because they died, or 1, 2, 3, etc. Is every one of these one of these? And yes, that is true. Some of these types of numbers are these types of numbers. We could say some rational numbers are whole numbers. So rational numbers are things like 1/2, 0.25, and also all the integers. And are some rationals whole numbers? Like 0, 1, 2, 3. I really suggest writing down these examples of the types of numbers so that you really remember what they are. So here are some of these over here. Yes, there's a 0 here, which is here. There's a 1 here, which is here. A 1/2 is not here in the whole numbers, but that's okay because it says some, which means, hey, some, which means 1 or more. And every means all of these are here. So this is still true. The union meaning putting 2 things together, the union of 2 sets are some other set. And we can say the union of natural numbers and whole numbers are whole numbers. The union of natural numbers, like 1, 2, 3, and whole numbers, like 0, 1, 2, 3, are whole numbers. So if I take these and put them together with those, we don't use repeats when we find a union and put them together. So if we mush those together, we will get these numbers, which are the whole numbers. So this is true. At some point, probably on your homework, you will find something that is false. All right. The intersection is where 2 sets cross over each other. So the intersection of natural numbers and whole numbers are natural numbers. So natural numbers like 1, 2, 3, and whole numbers like 0, 1, 2, 3. And these ellipses here means and so on are natural numbers. Like 1, 2, 3. So an intersection is where they overlap. So they both have 1, they both have 2, they both have 3. Since 0 is in the whole numbers but not in the natural numbers, it is not part of the intersection. A finite set. The set of, let's see, the set of integers from -1 to 3. The set of integers from -1 to 3 is a finite set, meaning that I can count them out. So these would be the numbers -1, 0, 1, 2, 3. It would not have the dots at the end because it doesn't continue on. These are integers, meaning they don't have any decimals after them. And hey, it goes from -1 to 3. There's 1, 2, 3, 4, 5. I can count them. It is a finite set. So that is true. Interesting thing. Something like the natural set goes on forever. So therefore, it's an infinite set, which cannot be counted. We're going to get to that here. The set of, let's see. Let's do the set of natural numbers, like 1, 2, 3, is a null set. A null set meaning that there's nothing in it. Obviously, there are things in it. That is false. The set of blank is an infinite set. If I did the irrationals, that would be things like pi, square root of 2, square root of 3, any of the yucky square roots and things like that. That's actually an infinite set because we can keep always finding a number that's bigger and bigger. All right, so that is true. Something is a subset of something else. So we could have our, let's see, integers. That would be like 0, 1, 2, and -1, -2. Are they a subset of the irrational numbers? The irrational numbers, remember, are things like pi and square root of 2 and square root of 3. Are these a subset, meaning inside of here? Well, -2 is not one of those numbers, -1 is not one of those numbers, 0 is not one of those. These are all nice, beautiful numbers without decimals and things like that. These are non-repeating, non-terminating decimals. So none of these are inside of those. So that is false. Now, I had a student who was struggling a little bit with the concept of subsets. So here I have the set of animals. Now, within the set of animals, kind of like we have the integers, we could have dogs. Are dogs a type of animal? Are dogs a subset of animals? Yes, they are. Are animals a subset of dogs? Are animals a type of dog? Not all animals are a type of dog. And then we can have a set next to it, which are cats. This would be like your rational numbers and your irrational numbers. There's this line between them. Can a cat be a dog? No. Can a dog be a cat? No. Can a cat be an animal? Yes. Are some animals cats? Yes. Are all animals cats? No. And so this helped out. And then we could have things like a specific cat. And so we can say, hey, is this specific cat a cat? Yes, it is. Is every cat this specific cat? No, it is not. So if you have a cat at home, it is one of a set of cats. It is one of the animals, but all animals are not your specific cat. So hopefully that will help you out. Chapter 1, Section 2, question number 2, unions and intersections. We're given two sets. A set is going to have these squiggly braces around the outside. We have set A, which has the elements 3, 6, 7, and 9, so each individual piece is called an element, and the elements of B are 1, 2, 3, 5, and 9. And we have to find this symbol and this symbol. This means A union, meaning putting it together, B. And A union B is equal to, we're going to write it as a set, so again we're going to start off with the squiggly brace, and we're going to write these numbers in order by union. We're going to put them together. So the smallest number is 1, then 2, then 3, then looks like 5, 6, 7, and 9. And then we have to find this one, which is A intersect B. Intersection, so a union puts them together, and an intersection shows where they cross over each other. So the intersection of these are just the numbers that repeat. So over here, there were 8 numbers. Nope, there were 9 numbers. And so here, we didn't get all 9 numbers. And the reason is, some of these repeated from this set to this set. So we have the 3 in the first set and the second set, and the 9 in the first set and the second set. That's why when we have 9 things up here, we only have 7 down here, because 2 of them were repeated. And we're going to note those 2 by saying that 3 and 9 are in the intersection. Now, a few students get confused on these symbols here. So, this U is for union, which is putting them all together, and this is an N for intersection. Which is where they overlap. Notice that at no point do we ever write, even though there's a 3 there and a 3 there, we never write 2 3s, we don't write 2 9s. We just write each number once, and we put these squiggly braces on the outside. Now, we teach math, not art. So if you can make beautiful braces, good job. Now, you cannot use a parentheses. That means something else. You cannot use a bracket. That means something else. But what you can use is you can use wagga waggas. You can be very, very fancy with your braces. And in the end, whether you do a regular brace, a sloppy brace, a really fancy brace, it really should not matter, because we are your math teachers, not your art teachers. Chapter 1, Section 2, Question 3. We're going to draw on a number line. So, here we have a number line, but it doesn't have any numbers yet. Many students just want to put a -3 someplace and a 2 somewhere else. But some, but not all of our college professors would like to make sure that you label all of these, so I want to make sure you're labeling all of these, because some students do not know how to label a number line. Ta-da! Label every single mark on the number line. You want them to be in consecutive order, meaning one after another. At some point in time, you will have to scale this, meaning you'll have to skip some numbers, but due to this part of the question here, we won't be doing it yet. There are 2 important numbers here, the -3 and the 2. So I'm going to put a circle here around above the -3 and a circle here above the 2. Some people do it on the number line. I find it a little harder to read, so I'm putting it above. And X, meaning what we're shading, this is the variable. It says X is in between -3 and 2. So I'm going to shade between -3 and 2. This also has an extra bar under it. That means less than or equal to. We did that by taking a less than sign and an equal to sign and mushing them together to get that. And the extra ink that makes that bar is the extra ink that fills in this dot here. That is done. But wait, this looks almost exactly the same, but it's not. It has 1, 2, 3, 4 things at the end that make it different. So once again, I'm going to have from -3 to 2, again, very important, I would like to make sure that you are labeling these marks. And this means and x is an element of the integers. So this is a funky looking C with a line through it that makes it an E for element of. If you think about it, the elements were all the different numbers. So these are elements of the integers. Our textbook uses I for integers and other textbooks use different letters. All right, so we want only the integers. It's not equal to -3, so I'm not going to write anything about that. But anywhere from here to here, all the integers. -2 is an integer. -1 is an integer. 0 is an integer. 1 is an integer. 2 is an integer. Ta-da! That is everything. From -3 to 2, not including -3, but yes, including 2, and all the integers in between. Chapter 1, Section 2, Question 5, Type 1 of 2. Many students consider this question to be the easier of the question 5s. So, we're going to do unions and intersections backwards. We're going to give you the union, we're going to give you the intersection. We're going to ask you to split it up into a set for A and a set for B. One of the reasons that this is difficult is there's many answers to this. Often, but not always. So if we look at this, one of the sets has to have a 3. One of the sets has to have a 5. But both of the sets have to have 6 and 7. So I have to make sure that 6 and 7 are in both sets. And one of the sets has to have a 9. That is an answer. There are many answers. You could have the 3 and 5 up here. Both sets have to have 6 and 7. And then the 9 could be down here. You could have the 5, 6, 7 up here, and then the 3, both of them have to have 6, 7, and the 9 down here. However, there is a trick that you can do, which is to just take the first set that you're given and define that to be set A. And just copy that over. And then define the second set to be set B. And while lots of students want to be creative and find their own answer to this is a very basic way of doing it. You just take the first one, call it A, take the second one, call it B. You'll get it right. Chapter 1, Section 2, Question 5, Type 2 of 2. Here, we're given a table, which could be a vertical table or a horizontal table, and it has 2 sets of people. In this one, it has Chapter 1, no calculator, and Chapter 1, calculator. And there are 4 people in each of these sets that have been defined. And we want to find the set of Chapter 1, no calculator people, and Chapter 1, calculator people. So we want to know, is Aaron in the first list and the second list? No, he's not. Is Henry in the first list and the second list? Yes, he is. So as we start making off our list, we're going to have Henry first. Is Stan in the first list and the second list? No, he is not. Is Vi in the first list and the second list? Yes, she is. So these are the people who are in the first list and the second list. If you think about it, in question 2, we actually covered this as part of our vocabulary. This is the intersection where the 2 lists cross over. So is this an intersection or a union? This is an intersection. Now, we want to find the set of all people in the first column or the second column. Hey, this was an intersection. The other one's going to be a union. We're gonna put all these names together. Think about it, when we were doing this with numbers, we had them in order from least to greatest. With words or names, we probably want to have them in alphabetical order. So, alphabetical order, no repeats, and also because you're going to be doing this on quizzes, tests, homework, things that you're going to be turning into your teacher, I would think that you would write out the entire thing without abbreviations. So trying to get this in alphabetical order, we have Aaron comes first, and then Henry, and Holly, and Joyce, and Stan, and Vi. Now, to double check, there were 8 names to begin with, 2 of which were repeats, so there should only be 6 names in our union. 1, 2, 3, 4, 5, 6, and we do. This is our union where we put them all together, but we didn't write any of the repeats twice.